Hey everyone, today we're going to dive into one of the most incredible ideas in all of physics, electromagnetic induction. Now, I know this is a huge topic, especially for your board exams, but don't you worry. By the end of this, you'll see exactly how it all clicks together. So let's get right into it.
So let's kick things off with a massive question, one that really puzzled scientists for a long time. Can you actually use magnetism to create electricity? I mean, they seem like totally different things, right? Well, the answer is a huge yes, and how it happens is, well, it's nothing short of genius.
All right, here's our game plan for today. We're going to start with Faraday's groundbreaking discovery. Then we need to get our heads around a key idea called magnetic flux. After that, we'll use two big laws, Faraday's and Lenz's, to figure out how much electricity we get and which way it flows. And to wrap it all up, we'll see how this is all working in the real world, in tech you use every single day.
Okay, let's go right back to the beginning. The discovery of this whole phenomenon wasn't some single eureka moment. Nope, it came from a bunch of really careful experiments done by the brilliant Michael Faraday and Joseph Henry.
The setup they used was, honestly, super simple. Just picture a coil of wire. Now, instead of connecting it to a battery, you hook up the ends to a galvanometer. And a galvanometer is basically just a super sensitive detector for even the tiniest little bit of electric current. So, no battery, that needle should be sitting right at zero.
So, for the very first test, we take a regular bar magnet, and we just hold it perfectly still right next to the coil. What do you think is going to happen?
And the answer is absolutely nothing. The needle on the galvanometer doesn't even twitch. So here's our first big takeaway, and this is crucial. A stationary, unchanging magnetic field does not create a current. But what if we add a little bit of motion to the mix? What if we take that exact same magnet and start pushing its north pole towards the coil? Now what happens?
This is where the magic happens. The instant that magnet starts moving, that galvanometer needle jumps. A current has just been created in that wire, seemingly out of thin air. This amazing effect is what we call electromagnetic induction.
But Faraday didn't just stop there. He noticed that if you pull the magnet away, the needle kicks in the opposite direction, meaning the current has reversed. Same deal if you flip the magnet around and use the south pole. So what's the ultimate conclusion here? It's that it doesn't matter if the magnet moves or if the coil moves. What matters is the relative motion between them. That's the trigger. That's the whole secret.
Okay, so we figured out that a changing magnetic field is the secret ingredient. But, changing is a little vague, right? How do we actually measure or quantify that change? To do that, we need a new concept, and it's called magnetic flux.
I want you to think of magnetic flux. We use the Greek letter phi for it, as just a simple count. It's the number of magnetic field lines passing through the area of our coil. So as the magnet gets closer, more lines pass through, and the flux increases. As it moves away, fewer lines pass through, and the flux decreases. It is this change in the flux, the change in the number of lines, that's what's actually generating the current.
Now here's a really neat trick. If our coil isn't just one loop, but has, say, n number of turns, the effect gets multiplied. The total flux is just the flux going through a single turn times n. This is a super important detail for when you're solving problems in your exams.
So now we have a way to describe the changing magnetic field using this idea of flux. The next obvious question is, can we actually predict how much electricity we're going to create? And the answer is a big yes, thanks to the law that ties this all together, Faraday's law of induction.
Okay, this is the core definition, and it's a huge one for your exams, so listen up. Faraday's law tells us that the induced electromotive force, or EMF, and you can just think of EMF as the voltage that pushes the current along, is equal to the rate at which the magnetic flux is changing.
And mathematically, it's beautifully simple. E equals delta phi divided by delta t. So what does this tell you? It means if you change the flux really fast, like by moving the magnet much quicker, you get a much bigger induced EMF and a stronger current. It's all about the speed of the change.
Okay, so Faraday's law is brilliant. It tells us how much voltage we're going to get. But there's a piece missing, isn't there? It doesn't tell us which way the current is going to flow. Is it going to go clockwise or counterclockwise? For that, we need the next piece of this puzzle, Lenz's law.
At its very core, Lenz's law is really all about the law of conservation of energy. You see, in physics, there's no such thing as a free lunch. You can't just get electrical energy for free. You have to do work. The current that gets induced actually creates its own magnetic field that pushes back against you, opposing your motion. And the mechanical work you do to overcome that push is what gets converted into electrical energy.
And this idea leads us to the formal statement of the law. You'll want to write this one down too. It says the induced current will always flow in a direction that creates its own magnetic field to oppose the very change that created it. It's like nature always trying to keep things in balance.
This chart makes it crystal clear. Look, if you push a north pole towards the coil, the flux increases. The coil doesn't like that, so it induces a current to create its own north pole to repel you and push you back. Now, if you pull that north pole away, the flux decreases. The coil doesn't like that either, so it induces a current to create a south pole, trying to attract your magnet and pull it back in. It always fights the change.
All right, let's take all this theory and apply it to a specific case that you will definitely see in your exams, motional EMF. This is just the EMF that's induced when a straight conductor, like a wire, moves through a magnetic field.
Let's look at a classic setup. Imagine you have a metal rod sliding along some rails, all inside a magnetic field. As that rod moves, the area of the loop it creates is changing, which means the magnetic flux through the loop is changing. And what does a change in flux cause? An induced EMF. Now, the full derivation is about balancing the mechanical power you put in with the electrical power you get out, but the final result, the formula you absolutely need to know, is super simple. The induced EMF E is just the magnetic field strength B times the length of the rod L times its velocity V. So E equals BLV. Easy as that.
Now, I know what you might be thinking. This is all just theory for an exam paper, right? Wrong. Electromagnetic induction is the engine running inside so much of our modern world. Let's just look at a few examples you probably use all the time without even thinking about it.
Ever wonder how a metal detector works? It sends out a changing magnetic field. When a piece of metal comes near, that changing flux induces a little current inside the metal, and that current creates its own magnetic field, which the detector then picks up. An induction stove is even cooler. It has a powerful, rapidly alternating magnetic field that induces huge currents directly inside the metal of your cooking pan, which is what generates all the heat. And your ATM card, when you swipe it, that magnetic strip moves past a tiny coil. And that relative motion induces a current that is literally the data from your bank account. It's all just Faraday's law in action.
So, what's the one big idea to take away from all of this? It's this simple but incredibly powerful statement. The universe has this fundamental rule. Whenever and wherever you have a changing magnetic flux, electricity is born. It's a connection that literally changed the world.